Hello everyone, in this video I'm going to talk about chapter 3.2 Fundamental Theorem and Antiderivation. Okay, so the fundamental theorems of calculus is the integral from a to b fx, the first derivative dx equals to f of b minus f of a. So take a look closely. So for this interval, the first part is the definite integral, where inside the function is the first derivative of the original function, which is the area that is from a to b bounded by the derivative of fx and x-axis. And this is equals to the original function from b minus the original function subtract a. Okay, so now let's take a look. I want you to find fx if you know that the derivative of fx equals to 2x. So you might have different answers for this one. So let's say the derivative is equal to x 2x. So that means the original function might be fx equals to x squared, right? Because you take the derivative of x squared equals to 2x. Or maybe fx equals to x squared plus 5. Because when you take derivative of a constant number, this equals to 0. So that means the derivative might still equals to 2x, or even fx equals to x squared plus or minus, let's do minus 3.3. So their derivative is still equals to x squared 2x, right? So that means what changed the function? Well, if you think about it, if you're adding or subtracting a constant of a function, the function is going to shift vertically up and down, right? But derivative, what? It's the slope of the function. Think about that. If you're shifting the function up and down, but it shouldn't change the shape of the function, right? So that means the slope will remain the same. So that means no matter what is the original function look like, you shift up or down, the derivative should be the same. So just think about that way. The derivative just tells us the shape of the function, not the location, because the up and down vertically tells you the location. So the antiderivative of a function is any function fx I should write it in antiderivative of a function fx is any function fx where f prime of x, the first derivative of the original function, is the lowercase fx. So this is the antiderivative function. So the antiderivative function of the little lowercase is the whole family of the function. So to be more accurate, like I showed you earlier here, the antiderivative function should be the original function plus a constant. The constant could be a positive number or negative number. C represent any constants. So at where the derivative of the original function is going to equals to derivative function. So the antiderivative function is also called indefinite integral. Remember last video we talked about that the derivative function is what definite integral. The antiderivative one is going to be an anti-integral. So the notation for a antiderivative function is going to be antiderivative f of x dx. That means it's antiderivative. So the sign look like x. This is still called integral sign. Integral sign. So we must include in this dx. That means we know which variable we're trying to antiderivative with. Okay, so now let's try this one. I want you to find the antiderivative function of 2x. Well, if I can choose any function that I like as long as the derivative is equals to 2x, right? So you can pick the original function equals to x squared plus 1, that's fine. Or fx equals to x squared minus 2. Because when you take the derivative of this function, this is going to equal to 2x. So that means the antiderivative function, they could be anything. If you want it to be more general, you can write it as the antiderivative function 2x at the variable x equals to x squared at a constant c. Okay, so now try this. Find the antiderivative of e to the x. Well, let's think about what function when they take derivative is equals to e to the x. It's going to be itself, right? So that means this is equal to e to the x plus c, because they might have a constant. So now let's recap again the fundamental theorems of calculus. So for the antiderivative from a to b at dx, this is going to equals to the original functions at b minus the original function at a. So if we manipulate the function a little bit, so that means we add f of a on the same side. So we will have f of b equals to f of a, the original function, plus the antiderivative from a to b at dx. So what does the application for this one? Now let me show you an example. Now take a look at this function. Suppose f of t has the derivative f of t shown below. Suppose that we know that f of 0 equals to 5. Find the values from f of 1, f of 2, f of 3, and f of 4. Well, if you take a look at here, we know that f of b equals to f of a at the integral from a to b at dx. Well, in this case, our f of 4 or f of 1, I can write it as f of 0 plus from 0 to 1 the derivative function. Okay, so the derivative function is equal to what? The area bounded by the graph x-axis, x equals to 0 and x equals to 1, right? So that means it's going to be the little triangle. So I know that f of 0 equals to 5, and then the little triangle bounded by the graph x-axis, x equals to 0, x equals to 1, is equals to 1/2. The base is 1 and the height is 1. So that means f of 1 is equals to 5.5. So we used a similar method to find f of 2, which is f of 0 plus from 0 to 2 the derivative function. So f of 0 again equals to 5, and then f of the integral from 0 to 2 is equals to the bigger triangle, which is the base is 2 with the high is 1. So that means f of 2 is equals to 6. All right, so what about f of 3? f of 3, we use the same method. We have from 0 to 3 f of t dt. So f of 0, again, 0. From f of 3, they have a two-part. One is the positive region, which is what we get earlier is the upper triangle. The other one is, you can think about is a lower triangle. That means you need to subtract that area. So I will have 1/2 times 2 plus 1, the positive area, minus the negative area, which is 1/2, 1 times 1, which is, oh, not 0, I'm sorry, f of 0 equals to 5. 5 plus 1 minus 0.5, which is 5.5. So you may think there's another way to do it. You're correct. So since we already have the answer of f of 2 earlier, so maybe we can start in from 2 to 3, because we can define f of 3 equals to f of 2 plus the integral from 2, which is the area from 2 to 3, bounded by the graph f of t, dt, and x-axis. So f2 from our earlier, we know that it's equal to 6, plus what? The area is negative, right? So that means I have to subtract a negative number, and this is a little triangle with the base 1 and the high 1. So you will get the same answer. So let's use this way to find f of 4. So f of 4, I can define it, instead of starting from f of 3, I can starting with instead of starting with f of 0, I can starting with f of 3 plus the integral from 3 to 4 f of t dt. So f of 3 from what we found earlier is 5.5, and then f of 3, the integral from 3 to 4 is going to be a negative, a square. So it should be negative 1 is a rectangle times 1, which is 4.5. So that's f of 4. So here's another example. So this is the graph shows the function f of x. The little f means that's the derivative of the original function. Okay, so the rate of change of fx, use that to sketch the original function f of x that satisfy f of 0 equals to 0. Okay, so now let's take a look at this function. The function from 0 to 1 is positive, and then from 1 to 3 is negative. So by our observation, the graph from the interval 0 to 1 is positive. And then that means if the derivative is positive, that means our original function f of x is going to be increasing function. Okay, and then at x equals to 1, the function is equals to 0. So that means at the original function, this point is either maximum or minimum. It's going to be an extrema. We don't know that. And then from the interval 1 to 3, the derivative function is a negative function. So that means the original function is going to be a decreasing. And then at x equals to 3, the function is equals to, the derivative function equals to 0. So that means there is a maximum or minimum. And then after 3 to infinity, the function is going to be positive. So that means it's going to be increasing. All right. So now, based on this information, we can draw the graph. We know that the graph at x equals to 0, the original graph. Now we're doing the original graph. Start with 0. We have 1, 2, 3, 4, 5. Okay, at 1, we're starting at 0, and then it's increasing, increasing, increasing. At 1, we know that there's going to be either maximum or minimum. We don't know yet. But we know that, hey, after 1, the function is going to decreasing. And then at 2, it's still decreasing. And then at 3, the function hits 0. And after 3, the function goes up, increasing. So this is approximately what the function looked like. So that means at 1, the function is going to be a maximum. At x equals to 3, the function is going to be a minimum. So now let's take a look at this example. So let fx equals to the integral from 0 to x, little f t dt, where f is graphed below, and estimate f prime and 3. So by the fundamental theorem, we know that, hey, if ax equals to the integral from x to x, from a to x ft dt, then the derivative of a of x, in our case, we use fx, dt dx is equals to the little fx. So that means our f prime of x going to equals to fx. So I have f prime of 3 equals to f of 3, and from the graph, since this is f of 3 graph, so this is equals to 0. Okay, so that's it for the fundamental theorem of calculus. Next time we will talk more about how to use that to find the antiderivative.